So for this experiment, we're going to measure the mass increase on the cathode after electrolysis using stoichiometry. So first we're going to weigh 6 copper strips. So that's the experiment set up in the diagram like this. So that allows us to do 3 trials in one go. So it is a setup of a series, so the current is the same throughout the circuit, so that we know exactly how many electrons go through each beaker. So hopefully you've covered this in junior science, V equals IR for series and parallel circuits, but just a quick reminder. So the voltage in series drops, but in parallel, the voltage in series splits, but in parallel it's the same. And for current in series, it's the same, but in parallel it splits. And for resistance, you add them together. For parallel, the total 1 over the total resistance is 1 over all the individual resistances. So hopefully that was just a quick review. Also just doing a quick review on the products of electrolysis. So you write all the cations on the side where the uh, they're going to get attracted to the cathode, the negative cathode, and all the anions on the positive side where they're going to get attracted to the positive anode, where they're going to get oxidized. And so the most positive one there is the copper. So the copper is minus 0.34, and the water is a lot more negative, minus 1.23. So the copper will be the one that gets oxidized. And on the right-hand side, the copper is plus 3.4, which is more positive than the water at minus, which is minus 0.83. So the copper will be on the right-hand side will be reduced. So you're going to lose copper and gain copper. So we've just reviewed products of electrolysis, what's going to happen on that front. And just the last thing there, the variable resistor just allows you can see V equals IR, so rearrange that to I equals V on R. So you can change the size of the R, make it larger and smaller, and that will give you a current. So if the current's too large or not large enough, you can change the resistor to bump up or lower the current to get what you want. Now, just going on from that, I've realized sometimes if the current is too high, always make sure you make qualitative observations. So that can help you interpret things for anomalous results or outliers. So outliers are errors. Anomalous results are trends that you didn't expect. And so, as you can see here with this picture, and at the end I try and bump it up a little bit, you can see that there's some black copper oxide forming at the cathode. In the past, I think I've bumped up the current quite a lot, and you can even get bubbles of H2. So just be aware that that's going on, so that there's other reactions going on that will cause your results to be possibly inaccurate, maybe systemic random errors. And materials fall off the cathode too, so it probably is a method improvement just to have the anodes because they seem to cleanly lose copper, whereas the cathodes might gain copper, but they don't do it very cleanly. So in this lab also, I decided not to use sandpaper because I didn't think the oxidation on the surface was very great, and not significant errors to have copper dust all around the room, which is a heavy metal. So I skipped that bit. I'm quite happy for you to skip that bit as well. Safety first. The variable resistor, and just a reminder too, hopefully you've covered all this in junior science. Ammeters are set up in series and voltmeters are set up in parallel. And so at the end, I just cleaned up the electrodes just by tapping them on a paper towel and leaving them for a minute or two, waving them. The method suggests you dip them in alcohol to remove all the water, and then the alcohol, or methylated spirits or methanol, will evaporate very quickly. But I didn't want all those sort of fumes in the room, and I didn't want to waste more chemicals. And so at the end, also don't forget to collect all your copper sulfate in a waste container. We often crystallize it out and reuse it, but it's toxic to aquatic life, so don't put it down the sink. So when you finish, polish up your data table. I've used Excel to calculate change in mass, average change in mass. Using average change in mass, I determined a percent difference to see if there is any justification for removing outliers. Here, the outliers are all over the place. It's not like this is one specifically bad one. So they're all spread out, so I left them all in. It's obvious at this stage that I should have done way more than 3 trials. because my results are all over the place. And absolute uncertainty of the mean is also in the table. Now, moving on to the calculations and uncertainty propagation, you can see that the really important thing here is instrument uncertainty. Now, even though at the very end I don't carry through my errors and do uncertainty propagation the full way, the reason I don't do that is because I get a nice analysis at the end. Whenever you do a percent error or a percent yield, you've sort of finished your chemistry experiment. You've got the answer and you know how accurate it is. And so I've done that there with 60%. But if I didn't have that, I would do my uncertainty. If I was just looking for a mass as my final answer, I would carry my uncertainty propagation down to here. But it's not really relevant. If I do carry that plus or minus 13 all the way down and ignore this one, which is a very small error, um, then that tells me there's a plus or minus 13 error on this basically, um, on these things, and I can get it up to 77%. But I decided to leave that out because it was unnecessary complication. But you can see a lot of schools are skipping this bit, and you can see that they're way short. If you do it, your results are so much better because what you actually see is you can see that the ammeter is giving you a 26% error. The stopwatch is rather insignificant at a 0.2% error. So I'm doing just 1 second because uh, basically reaction times are about zero point 0.3 and you double it, so it's about 0.5 or zero point 0.6. So you can always be conservative. I always make it plus or minus 1 second. Um, and then, sorry, not the ammeter, the balance. So the balance is a 26% error, the ammeter has a 13% error, and the stopwatch only has a 0.2. Now, you're not going to know that if you don't do um, your instrument uncertainties. And so you're not going to start talking about using a video and getting a more accurate way of timing because it's irrelevant. It's 0.2%. What you're going to talk about is the balance. And you don't just talk about it. You use data values. You say, look, there's a 26% error on the balance. That's the main error for this experiment. Um, so what I need to do is maybe use longer times to get larger mass changes, and also use a MATLAB balance to get the extra decimal place, and maybe that'll reduce it down to 0.2% as well. Same with the ammeter, it was very crude, it was an analog. Easily get a couple more decimal places and reduce that 13% to maybe less than 1%. And you can see if most of the schools have dropped this, and you can lift the level of your report way above theirs because you actually understand where the true errors are. Use those numbers and then show that you are making changes that will make significant improvements to reduce those numbers. Okay. So that's the huge importance of not just doing absolute uncertainty and mean, doing instrument uncertainty as well. In the end, you choose whichever one's larger, and in most cases, you do uncertainty propagation all the way through. I left this one out because I had percent yield, which gives me an overall end view of how accurate we are. So that gives me an accuracy number, and I don't need to take this one further in this case. Okay, hope that's helpful.